Good afternoon, everyone. My name is Mingwen, and I'm from Huazhong University of Science and Technology, China. It's my great honor here to present our work today, Historical Spectrum-Based Fault Localization. And this is a journal first paper, and which is cooperated with the other 5 institutes. Spectrum-based fault localization is important and a popular debugging technique that can help developers in locating bugs automatically. It has also been widely incorporated in automated program repair techniques. The basic intuition is that those code entities covered by more failing test cases, but less passive ones, are more likely to be the root cause of the bug. However, it also suffers from 2 major limitations. The first is that the test coverage information cannot reflect the root cause of a bug directly, which is simply an approximation of the bug. The second is that it suffers from the type issues significantly, in which case the code entities within a SAM block cannot be well differentiated by existing techniques. Therefore, it motivates us to look for other information for better fault localization. As we all know that software evolves by means of code commits. Here we show a concrete example of a project Apache Hadoop, and we can see that it receives plenty of commits per week. Those commits are committed to add new features, to fix existing bugs, to perform refactoring tasks, and so on. Besides, it can also introduce new bugs. We observe that developers are often looking for the information from evolution histories when debugging in practice. For instance, they often search for the code change that introduced the bug when locating the faults. Inspired by this, we further conducted a survey at Microsoft. We have received 109 valid responses in total, and here we show the distribution of the developers with different years of working experiences. The major findings of our empirical study is that nearly 76% of the developers agree that version histories are useful in debugging, and nearly 96% of them have ever leveraged the information of bug-inducing commits in the task of fault localization. However, nearly 75% of them conduct such process manually due to the lack of tool support. Therefore, it motivates us to leverage the information of version histories, especially the bug-inducing commits, to design better fault localization techniques. Based on these observations, we propose to build the historical spectrum along the version history. Suppose VT is the target version for fault localization. We first identify the bug-inducing change, which is a change that introduced the bug, and started from which the bug-revealing test starts to fail. We also identify other non-inducing changes and then build the historical spectrum. Our basic intuition is that those code entities modified by more bug-inducing changes but less non-inducing changes are more likely to be the root cause of the bug. However, there are 3 major challenges for us to build the historical spectrum. First, identifying bug-inducing changes from version histories is non-trivial. Second, mapping the code entities from the bug-inducing version to the target version precisely is a challenge. Third, changes are usually tangled with other irrelevant code modifications and large in their sizes. Therefore, even if we have identified the bug-inducing changes, precisely locating the buggy statements is still non-trivial. Here we show an example of a pie chart. It shows that the average size of the bug-inducing changes contains over 400 lines of statements, while the size of the associated fixing changes contains less than 4 statements. To address the aforementioned 3 challenges, we propose HSFL, which is historical spectrum-based fault localization. It mainly contains 3 steps. First, we identify the bug-inducing changes. Specifically, we leverage program slicing to minimize the logics of the test cases, and then perform binary search among the version histories. Second, we construct historical spectrum, which tracks the evolution of source code from the inducing version to the target version. Third, we rank all the suspicious statements by leveraging existing formulas such as Okaya, Tarantula, D-star, and so on. To evaluate the effectiveness of HSFL, we use the defix4j benchmark, which contains over 300 real software bugs. The defix4j benchmark has been widely used in the evaluation of fault localization and program repair. Evaluation metrics of top N, MAP, and MLR, 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 In our first research question, we evaluated the effectiveness of HSFL. Here we show the results measured in terms of MAP and MRR, and we found that HSFL is able to achieve an average improvement of 28 and 40% for MAP and MRR respectively on average. Similar results have also been observed in terms of the metrics of top N. As we all know that besides SBFL, there are many other different families of FL techniques, such as mutation-based, slicing-based, and so on. In this RQ, we compare HSFL with these techniques. Here we show the results in terms of MAP and MR. Such results indicate that the hybrid-based technique, SBFL, can achieve the optimal performance among all the baselines, and HSFL can outperform the hybrid techniques in terms of both MAP and MR. In our third research question, we integrate HSFL into no-need-to-rank techniques. As the results indicate, no-need-to-rank techniques can outperform HSFL and other families of fault localization techniques. Besides, while integrating HSFL, the performance of no-need-to-rank techniques can be further improved. Specifically, the MAP and MRR can be improved by 3.7% and 5.4% respectively. Here comes to the end of our presentation, and questions are welcomed.